In this video, we're going to do a conceptual question involving the rank-nullity theorem. The question says, let A be a 3 by 5 matrix, form a 3 by 6 matrix B by making the first 5 columns of B equal to the 5 columns of A, and making the 6th column of B equal to the sum of the 6 columns, the sum of the columns of A. Suppose that the nullity of A is 3. For each part, give the number that correctly completes the sentence. Part A asks for the nullity of B, part B is the nullity of A transpose, and part C is the nullity of B transpose. So take a moment and try to answer this question. Okay, let's go over the answer. So A is a 3 by 5 matrix. So let's just write it out. It's a 3 by 5 matrix, 3 rows and 5 columns. And what you do to form B is, so let's call the columns V1 through V5. Then B has columns V1, V2, V3, V4, and V5. And then the 6th column, V6, is V1 plus V2 plus V3 plus V4 plus V5. Right? So the problem says that the nullity of A is 3. And part A asks for the nullity of B. So we want to think about the rank of the matrix. If the nullity of A is 3, remember that means the dimension of the null space, then what's the rank of the matrix? Well, A has how many columns? 5. And the nullity plus the rank must equal the number of columns. That's the rank-nullity theorem. So the rank must be 5 minus 3, which is 2. So A has rank 2. That means that A has a maximum of 2 linearly independent columns, and then it has 3 columns, which are linear combinations of those 2 columns. Now, if you look at B, okay, B is a 3 by 6 matrix. It has 6 columns, but notice that the last column is a linear combination, right? This last vector, V6, it's a linear combination of the 5 vectors V1 through V5. So the rank of B, okay, if you start off with the matrix A, it has 5 columns, and then B, you make a new matrix with 1 additional vector, then the rank is either going to stay the same or it's going to go up. I mean, one way I think about this is that it's the dimension of the column space. So you have more columns, you have more column vectors that you're looking at the span of in B. So the dimension of the column space is either going to be equal to the dimension of the column space of A, right? It's going to equal the rank of A, or it's going to be 1 more. It's going to be the rank of A plus 1 to get the rank of B, if V6 is not a linear combination of the previous columns. But in this case, V6 is a linear combination of the other columns. So what happened to the column space of A when going to B? The column space stayed the same, right? It's the same column space. So it has the same dimension, and that's the rank of the matrix. So the rank of B is the same as the rank of A. Okay, so the rank of B is also 2. And so what does that mean about the nullity of B? The nullity of B is, well, it's the number of columns, which is 6, minus the rank, which is 2, so the answer is 4. I think the most difficult part of this is understanding why the rank of B is the same as the rank of A. But this is an important thing to understand conceptually, right? You look at the span of the 5 vectors, okay, V1 through V5, That's some space, okay? And if you throw in V6, if V6 is in the span of those 5 vectors, then the span didn't get any bigger. So the dimension of the space is the same. Okay, part B says, what's the nullity of A transpose? So A is a 3 by 5 matrix, right? So therefore A transpose is a 5 by 3 matrix. It's the 5 by 3 matrix whose rows are V1 through V5, 5 by 3 matrix. But the important thing about the rank, okay, how is the rank of A related to the rank of A transpose in general? If you just have a matrix A, okay, it has a rank, there's A transpose. You can always transpose a matrix. That matrix, A transpose, also has a rank. How are those two ranks related? They're equal, right? That's a general fact. The rank of A transpose is equal to the rank of A. So the rank of A transpose is, in this case, 2, because we saw that the rank of A is 2. Now, why is the rank of A transpose equal to the rank of A? Well, it depends on how you're defining the rank of a matrix. But if you think about the rank as the dimension of the column space of A, say, okay, one of the important facts is that the column space and the row space have the same dimension. Now, if you take the columns of A, right, what happens when you form A transpose? What happens to those columns? They become the rows of A transpose. So when you look at the row space of A transpose, okay, that's the column space of A, right? The column space of A is equal to the row space of A transpose. And so the dimension of the column space of A is the dimension of the row space of A transpose, because they're the same space. And the row space of a matrix is the same dimension as the column space, right? The dimension of the row space of a matrix is the rank of the matrix. So the rank of A transpose is the rank of A. That's just true no matter what matrix A is. Okay, if you write down any matrix whatsoever, that matrix and its transpose have the same rank. So the rank of A is 2, and so therefore the rank of A transpose is 2, and therefore the nullity of A transpose is, well, A transpose has 3 columns, 3 minus 2 is 1. Okay, so the answer is 1. Finally, what's the nullity of B transpose? Well, this is similar to what we did. The rank of B is 2, so the rank of B transpose, which is the rank of B, is 2. Now B transpose is a 6 by 3 matrix, so the rank so the nullity of B transpose is 3 minus 2, which is 1. So the answer is 1. Okay. I think this is a really good question to test your understanding and to develop your understanding of the rank-nullity theorem, because this has no concrete vectors whatsoever, right? This is a problem with no specific vectors, but it's the concepts. It's understanding the conceptual aspects of the rank-nullity theorem, what it's really saying. And this is a good problem of making sure that you understand the general concept.